So thank you for tearing your way yourselves from the US election coverage. I hope none of you have developed ulcers or are feeling in other ways sick or disgusted with the state of the world. It is a pleasure to not be watching it and instead be introducing Shanika. Shanika did her honors degree at Monash, working with Duncan Galloway. And then in 2019, she joined the Gravitational-Wave focus part of the group, working with me and as a member of the LIGO collaboration. Over the past, what is it now, 9 months, Shanika? She's been a member of the paper writing team for a LIGO analysis that just came out last week. And she'll be telling us about these results today. So Shanika, please take it away.
Thank you, Eric. So I will just share my screen. Can everybody see this?
Yes.
Perfect. Oh, spoilers. I can click back. Cool. Okay. So good afternoon, everyone. Thank you for the introduction. So yes, I'm Shanika, PhD student here at Monash University. And today I'll be presenting the exciting results from one of the latest LIGO and Virgo papers, population properties of the compact objects from the second gravitational wave transient catalog. So where to start? I say probably from the beginning. So if we look back to our first gravitational wave catalog, from the first and second observing runs 01 and 02, we had 11 compact binaries, 10 of which were binary black holes and 1 a binary neutron star. And if we fast forward to 2020, and we include the observing run from the first half of 03, or the third observing run, we have 50 compact binaries, 47 of which are confident detections. And of those 47, 44 are binary black holes, 2 are binary neutron stars, and we have 1 possible neutron star black hole merger. And so when you have a lot of events, what's interesting to do is analyze the population. And so for our population study, we used the 44 confident binary black hole detections. So when you have a lot of events, you want to understand things about the population. So some of the key questions that we want to ask ourselves are there very massive binary black hole systems above 45 solar masses, for example? Do we have a preference for mass ratios close to 1, so meaning that our black holes are of similar mass when they're in a binary? We want to know how the merger rate evolves with redshift, how fast these black holes are spinning, and whether they're spinning in specific directions, and things such as the minimum black hole mass. These are just some of the questions we want to answer, and we can do these kind of things with population analysis. So there are a number of aspects that I'll go through, but the talk is really split up into 2, focusing on mass and then spin later. So let's start off with understanding the mass distribution. So what we want to do is understand what this distribution looks like. Are there features that are very distinct? And so we can do this by using different mass models and comparing our population to those models. And I'll go through an example of a few of the ideas behind the models that we use. So first of all, what happens at the low end of our black hole mass distribution? Well, one of the questions we can ask is what's the minimum black hole mass, which we can determine from our mass distribution. But we can also start asking questions about whether there's evidence for a gap between black holes and neutron stars. And more specifically, given that we're looking at black holes, we can try and understand what the end of the mass distribution looks like. Is it a sharp cutoff, like this purple curve, or a more smooth cutoff? And this can give us information about what the end of the distribution looks like, and whether there's potentially a dip in the distribution. Another thing that we look for in our analyses of these black holes is this peak at around 40 solar masses. So this is motivated by pulsational pair instability supernova. To describe this in a short amount of time, essentially you have these stars ranging from really massive stars ranging from 80 to 130 solar masses at zero age main sequence, ZAMS. And these stars shed their mass in pulses. And as they shed this mass down to masses less than these 80 solar masses. And so you have a range of stars that have now become to similar mass stars, and they undergo a supernova and collapse down into a black hole. And so you're producing a lot of black holes at around this mass range, and this mass range is around 35 to 45 solar masses. So we expect a pileup of black holes at these masses. So if you have a mass distribution, we expect to see some sort of peak-like structure in the mass distribution to represent this pileup of black holes. So this is another thing that we look for using our models. Another thing to consider is what's happening at the high mass end of this mass distribution. So is there a cutoff? And we ask this question motivated by pair instability supernova. So beyond the masses from the previous scenario, we expect the supernova to not pulse, but rather when they undergo a supernova, they will completely explode, leaving behind no remnant, no black holes. So, which means that we would expect some sort of cutoff at the end of the distribution, whether it be really sharp or it might be a bit more smooth. But we expect there to be no black holes beyond 45 solar masses if we consider just this process. But what you may know is that GW 190521, which was the most massive event detected to date in our gravitational-wave catalog, this is considered to be what we call a hierarchical merger, which would allow for things beyond 45 solar masses. So what this involves is you have two black holes, they merge, and then they might merge again with another black hole. So on the right here, I've just denoted these black holes merging and merging again and merging again. So we call them first, second, third, and fourth generation black holes. So you can consider high mass black holes to be hierarchical mergers, but the true smoking gun for hierarchical mergers would be to see a correlation between mass and spin, specifically because if when you have black hole mergers, as they merge, they inherit the angular momentum from its parent system. So as you continue to merge and merge again, you'd be obtaining more and more angular momentum. So you'd expect these systems to be spinning faster as you become more and more massive. So this is something we look for as well. So here are some results. So first of all, let me describe what these models are. So we have 4 mass distribution models. Note that we do have another one, but that's combined with spin that I'll discuss later. But here we have 4 models, one which is a simple power law, so truncated, being a simple power law with sharp cutoffs. Then we have what we call power law plus peak, which is a mass distribution that doesn't have a sharp cutoff at low masses, rather it's smooth. And we also have a peak-like structure in the distribution. Then we have broken power law, which also has a smooth lower mass end, but instead of a peak, we have a break between 2 power laws. So these power laws have 2 different slopes, and so there's a break when they meet. And finally, we have this model called multi-peak, which, as the name suggests, has multiple peaks. So we have smoothing at the low mass end, and we have a peak and another peak. So I've placed some ticks next to some of these distributions, and they're the ones that are preferred from our analyses. So we have a preference for a peak-like structure and a preference for a break-like structure. And our multi-peak model is also moderately preferred when compared to, say, truncated, but it's less preferred than power law peaks, suggesting that there's not enough evidence or support for a high mass peak. So moving right along, let's talk about the different regions of this mass distribution. So let's start at the slow mass end. Here on the right, I have plotted the minimum mass, so the minimum mass of the black hole, plotted against this delta M parameter. Delta M models how smooth that cutoff is at the low mass end of the mass distribution. So delta M0 means you have a sharp cutoff, and delta M larger than 0 means you're getting smoother and smoother. So what do we see here? You'll notice that in the bottom left-hand corner, we don't have any support for this region of the parameter space. So we don't have support for very small black hole masses with a sharp cutoff. So what we're seeing here is either we have a sharp cutoff at around 5 or 6 solar masses, or we have a smoother distribution or smoother slope or cutoff at lower masses. So this seems to suggest that there might be some sort of structure there. And what we're really starting to resolve is this potential low mass gap. Down the track, we may be able to resolve this further with more detections, but at this stage, we're getting hints of some structure there. So that's very exciting. So speaking of low mass objects, we consider some analyses using or including GW 190814. So this event was the possible neutron star black hole system, but it may also be a binary black hole. We're not sure. So we wanted to understand what happens to our population if we include it, if it's a binary black hole. And so I will start with the right-hand plot over here. So this is the distribution of the primary mass of the black holes, primary mass being the larger black hole in our binary. And without 190814, we have a distribution that has a turnover at around 6 to 7 solar masses and continues on. When you include 190814, this turnover is at lower masses, at around 2. And this is highlighted here on the plot on the left. Here we plot the minimum mass distribution for different mass models. The shaded ones represent the minimum mass without 190814, and then the non-shaded represents with 190814. So including this event significantly shifts our minimum mass. The fact that it shifts this position of the turnover suggests that including this event and our model isn't really a good fit with this event, suggesting that it's an outlier to the population. Another test we did was consider how likely it is to draw this event from our current population, and that probability is less than 0.02%. So when we use this event, it seems like it is an outlier compared to the rest of our population. So for our default analyses in this population study, we exclude this event. Moving on. So 190814 happens to be also a very extreme mass ratio event, from a mass ratio of 0.1. Another event in our catalog that has a mass ratio that's confidently away from equal masses is 190412, which is a confident binary black hole. And we find that this event is confidently away from Q equals 1 at 99% credibility at Q equals 0.55 when considering our population. We also find that if you consider our population with and without 190412, there's a 50% overlap in these distributions. What this suggests is that this event is likely not part of a separate subpopulation, rather it's part of this population that we currently have, and it's just in the low mass end, or the low mass ratio end of our distribution. So in our mass ratio distribution, we don't see subpopulations of systems. So we've talked about the low mass end and mass ratios. What about the structure in our mass models? Well, I described before, we had two models that were preferred, this peak model and this break model. And here on the left, I have plotted the fraction of binaries in our peak. So we have a power law plus a peak in our model. And so this tells us the fraction of binaries we expect to see in that peak. And we see that the fraction is away from zero. It has support away from zero, which suggests that there is this structure of a peak. Similarly, if we look at the right plot, this is a plot of the two slopes, alpha 1 and alpha 2 represent the slope index of our two power laws. And majority of the support is away from equal slopes. So meaning that it's showing that these slopes are different. They're not the same. So it suggests that there is support for this break-like structure. So our conclusion here is that our mass model or mass distribution isn't explained by just a simple power law anymore. Cool. So we talked about structure. What about the high mass end? So we find that actually there are masses beyond 45 solar masses. And in fact, even without including, so here on the right, I have the primary mass distribution with and without 1905-21, the most massive event in our catalogue. And here, even without this event, it extends beyond this 45 solar mass region. And this is likely due to hierarchical mergers. And this is something we investigate. And with 1905-21 thought to be a hierarchical merger. So rather than this sharp cutoff, we see this kind of tail in our mass distribution. So we do an analysis to search to see if we have hierarchical mergers. And this is related to finding a correlation between high mass and mass and spin. So we want to see if there are subpopulations in our population that distinctly have higher masses and higher spins. And what we find is there are hints. So here we have the mean of the spin distribution for two subpopulations and the variance of that spin for two subpopulations. So the different colors represent two subpopulations. Even though there's a slight difference, the measurement of error here between the distributions is large enough that they're consistent with each other. So unfortunately here, we don't have any clear evidence for hierarchical mergers in our population. So that ends the mass segment. Let's move on to spins. So another thing we want to look for, or a thing we can look for in our population analyses of binary black holes, is the spins, and this can give us hints as to how they evolved. So for example, we have what we call isolated and dynamical binary evolution. Isolated binary evolution is when you have two stars, they're in a binary together, they live their lives together, and they undergo supernova explosions, become black holes together, and eventually they merge. And so the key thing here is they've lived their lives together, they tend to have aligned spins. They tend to have similar spins to each other, or their spins tend to be oriented in the same direction. They tend to be aligned. So we have these spins becoming aligned over time due to tidal effects, and they evolve and eventually merge after they've become black holes. And so we expect their spin orientations to be 1, where theta is the angle between the orbital angular momentum and the spins of the black holes. We also have dynamical binary evolution. In this case, these binaries become black holes separately and then happen to merge, will capture each other and merge. So they didn't live their lives together. And so in this case, their spins can be randomly oriented. So this means that when they become a binary, there's no reason why they should be aligned. And so if we have, and if this is the channel in which all binary black holes are formed, we would expect an isotropic distribution in spin orientation. So meaning that we don't have a preference for a particular orientation of spin. So what do we see? We have evidence for misaligned spins. So misaligned spins being spins aligned, that are not aligned. And particularly we have spins that have what we call a negative chi-effective. So here on the right, I have a plot of chi-effective, and essentially what this is that below zero suggests, or is that the spins of your binary is anti-aligned with respect to the orbital angular momentum, and positive chi-effectives are aligned. So we have evidence for this misalignment or anti-alignment. And over here, I have the mean of the distribution of chi-effective and the sigma of chi-effective. So this points at evidence for misaligned spins. And advancing the slide, we've also, on the right here, we've calculated the fraction of chi-effective values that are positive and fraction that are negative. This is just to confirm that we do have negative chi-effective spins. So in fact, we find that 12 to 44% of the black hole population is tilted more than 90 degrees from the orbital angular momentum. So this really hints at evidence for dynamical binary evolution, assuming that misaligned binaries are dynamically formed, or a hint at dynamical evolution. So we do have evidence for misaligned spins, but we also have a preference for aligned spins. So if we look at our population, here on the right, I have this cos theta against, or the probability distribution of cos theta, and you'll see that majority of the distribution, or the highest probability, is at 1, which 1 equals perfect alignment. And so there is a preference for aligned spins, which is what you would see if your population was evolved through the isolated channel. So what does this all mean? Well, we have evidence for misaligned spins, and we also have a preference for aligned spins. So again, assuming that systems that are oriented more than 90 degrees from the orbital angular momentum, this suggests that there are evident, and assuming that more than 90 degrees means dynamical interactions, this suggests that there's evidence for both channels in our population, which is quite exciting. So we have evidence for binary black holes being formed through both the isolated and dynamical evolution channels. Another exciting result from this population study is the clear evidence of spin-induced precession. So precession is a result of when you have non-zero components in your in-plane spin. So you can have spins that are perfectly aligned with the orbital angular momentum, or you can have some component in plane. And if you have a component in plane, you get precession. And so what we find here is, so this is the mean. So on the right, I have a plot of the mean of the in-plane spin component against the variance, or sigma error of the in-plane spin component. And you'll notice that the 0 point in this distribution is excluded. And this is excluded at 99% credibility, which means that you do have in-plane spin. And if you have in-plane spin, you have precession. So this is a really exciting result from this paper. And we have clear evidence of precession from a population standpoint, which is very exciting. So to pretty much almost at the end here. So here we also have updates for the merger rates of both binary black holes and binary neutron stars, and they're quoted here. And note that here, so here on the right, I've plotted redshift against the merger rate density, and this dashed line represents the star formation rate, and this curve represents, so the solid line is the average, and the shaded regions represent the confidence intervals, or credible intervals, sorry. And you'll notice that this evolves slower than the star formation rate density, but is consistent with it. So we have so we've updated these merger rates with this catalog. And so to summarize, we see features beyond the power law in our mass distributions. And specifically, we don't see sharp cutoffs, and we see evidence for a peak-like or a break-like structure in the mass distribution. We have clear evidence for spin-induced precession. Awesome. We have preference for aligned spins and evidence for anti-aligned spins. So this supports the idea that we have both isolated and dynamical evolution for binary black holes. We have no clear evidence for hierarchical mergers in the population. I'll emphasize the yet, because there may be a paper coming out very soon from some LIGO colleagues on this very topic. And we've updated the merger rates for binary black holes and binary neutron star mergers. So all this work would not have been possible without members of the LIGO collaboration, particularly the paper writing team. So may I introduce you to the core paper writing team of this paper, which includes myself, Eric, Colm, who is a PhD student here, and Maya, Dan, and Tom. So the 6 of us have been working together for a long while to get this paper done. And so we're absolutely delighted that it's out there for everybody to look at, analyze, and we're excited to see what the community does with all these results. So thank you for listening.
Thank you very much, Shanika. So virtual round of applause from us. Yeah, it's very amazing that like until about 5 years ago, people were quite skeptical about gravitational wave detections, and now we have 50 of them and can do proper population studies.
For sure.
Yeah.
Very exciting.
Yeah. So is there any questions for Shanika from the audience? Please write in the chat box or raise your hand. In the yes, Ulrich, please.
Yeah, you talked about the spin alignment. And first, just a question I don't quite not quite understanding. You have 2 black holes that are merging.
Yes.
So when you talk about the spin alignment to the orbital plane, what is it you actually mean then?
So you've got the individual spins of the compact objects in the binary, and then you've got the orbital angular momentum. So the spin alignment would be the individual components are aligned with the orbital angular momentum.
Okay, so you kind of get 2 results, if you like, from each merger.
Yeah, from both compact objects, yes. Like we have the spins from both compact objects, and we look at the overall alignment.
And then the question, okay, so I understood that correctly. Then the question related to that is that on your little drawing you had a kind of a thing that you jumped across where you talked about that the supernova potentially will give a kick to it. You just went past it there. So is that from modeling that you then have to figure out what that kick is, i.e. how misaligned would they be even if they were in an isolated binary evolution?
So we expect these kicks to be quite small compared to, well, the kick to be small in the sense that it doesn't completely misalign our individual components. I imagine we don't actually model for that in our analysis or anything like that, but the assumption is that the kicks won't completely misalign these objects.
Okay, thank you.
Okay, Ilya has a hand up.
Hi, Shanika. Thanks for the very interesting talk. I actually have a number of questions, but I'll ask one right now, and then we'll see if there's time to look back for another one. So one of the interesting questions that one of the interesting results reported was about precession measurements. And you reported that you were confident that the population does not support a precessing spin of 0 for all of your systems. Now, if I understand correctly, the way that you do the population modeling is that you start with your individual posteriors that were obtained for individual events using the standard LIGO analysis, and then you reweigh them according to the priors for the population. The problem is, if I understand correctly, that the posteriors, that the analysis for individual events places a prior that is actually 0 at a precessing spin of 0, which means that I would imagine that you have no posterior samples or very few posterior samples anywhere in the region right around a precessing spin of 0. And does that create problems when you're trying to then do a population model allowing for precessing spins near 0? So basically the reweighting procedure either has too few samples to reweigh, and then when it does reweigh them, the weights end up being very high because you're dividing by the prior used in the individual event analysis, which is very low there. So does that mean that you're very sensitive to those few samples that you have in the region of interest?
So I think so, yes, indeed. I guess the initial priors, I'm just trying to remember how, I guess the parameterization we use is using samples from the spin magnitudes. I'm just trying to remember how we did the analysis, but I imagine that if you consider, you know, the width of the mean as well, we would still expect support in that region of parameter space, given that the width is also excluded.
Shanika?
Yeah.
Is it okay if I jump in to help with this one?
Go
This analysis is done by Tom Callister and Will Farr, and I think the way that they did it is they fit the posterior samples from individual events to the KDE them so that they got support. They're basically not recycling for this analysis so that you can have support near small values of chi-p. And there was, as part of the review, they did tests where they injected simulated signals drawn from distributions that were that would not have had precession because everything was aligned but conditioned on the same Q values we got, and check that they did not have false detections of precession using the method that they devised to do this measurement. So I think that by KDEing it, you can get around the sample density problem that you are worried about. But that is something you have to consider. And that we did as well do Tom and Simona Miller, who was working on this as well, did do tests, which actually Isabelle helped oversee on the review team to check that they didn't have false positives.
Thank you. Okay, so what you're saying is that basically you do have in the end, okay, that sounds great about the tests, and I guess you have enough events then where even at low values of chi-p, there is significant difference between posterior and prior, so that your likelihood, your data point you towards low chi-p values being disfavored. And so even though individual events do not successfully rule out 0, the combined evidence for a disfavoring of chi-p on a significant subset of the events, low chi-p on significant subset of the events, is enough to push you towards a preference for higher chi-p. Is that a valid statement?
Yeah, I was just waiting to see if Shanika would shake her head as well. But yeah, the slide that Shanika has up is I think supporting that. And if you make the same version but with simulated signals but conditioned on the same mass ratio, you get that peaking at at a mu and sigma value, or actually you get it consistent with mu is 0 and sigma equals 0, which is what you need to have in order to get no precession, because if either of those is non-zero, that suggests there's precession.
Thank you.
Okay, so we have hands from Rosemary, Bernard, and Nikhil. So Rosemary, please go ahead.
Hi. Yes, with regard to this alignment and precession, I would have thought that no matter how a binary pair comes into existence, either from primordial binary or dynamically, that there'd be apart from a direct collision, that there'd be time for, just like orbital circularization, alignment, spin alignment to occur due to the emission of gravitational waves, that the damping effect on the binary. So can you comment on that?
So I imagine that with dynamical evolution, the time frame in which, like, if there is any alignment effects, the time frame in which it emerges versus the time frame it takes to align.
The time scale.
Yeah, the time scale would be very different enough for us to be able to see these misaligned spins, rather than.
Well, it implies that. Well, yeah, it implies that, or that there's some more interesting effect going on due to the relaxation process. I think we probably see this in normal stars too. Some stars are misaligned, or even anti-aligned, or even perpendicular to the orbit, and they're primordial binaries. I think there's probably I suspect there's more to it than just simple dynamical formation. Anyway.
Yeah, well, to emphasize the fact that we're assuming that these misaligned spins are indicators of dynamical formation. Of course, the process could be more complicated than this, but
yeah, the time scale thing, you're absolutely right. It is a question of that, and so I guess my question really is, how can the time scales be that way around, except for direct or almost direct collision? I would have thought that there'd be plenty of time for.
To be fair, I've never actually thought of this question, so.
If I just jump in for 1 second.
Go ahead, Ilya. I think we're going to say the same thing.
Oh, sorry, Eric, please go ahead.
I think we're going to say the same thing. Please go ahead.
Yeah. Okay, doesn't matter. Yeah, so if you start with an isotropic spin orbit misalignment distribution, it remains isotropic under gravitational wave evolution for compact objects. So there's, unlike the eccentricity, which decays away under gravitational wave emission, an isotropic spin orbit misalignment distribution, although there will be slight changes, there will be, of course, precession and so on, but the overall properties of the distribution are actually conserved.
That's really interesting. That you don't get a lot, because in normal stars, that's you get circularization, spin synchronization, and alignment.
There's no tides though with
you don't get that with black hole. Isn't that beautiful? Wow.
There's Avi, I don't know if Avi's on the call, but he actually made a nice movie showing how the spin vectors of black holes evolved during evolution, and indeed, as the system processes, the spin vectors can do crazy things. But
yeah, I have seen that. Yes, so you need just a little bit of misalignment, I guess, to get that kind of crazy
but
stuff.
The point Ilya is making, which I agree with, is that they don't have a statistical tendency to align up. They do evolve, but they don't. They just keep doing their processing thing, but they don't have a preference to get aligned through that process.
There are a couple of small tweaks to that. So if you start with a distribution that's preferentially aligned, it does actually tend to slightly realign, very slightly, but an isotropic distribution will remain isotropic.
Fair enough.
Huh. Fascinating. Yes, I should look back at that. Exciting stuff.
Okay, thank you. So shall we move on to Bernard?
Thank you. I was going to ask, as an outsider, why is the existence of precession exciting?
So part of it is, I guess, well, why is it exciting to me? For me, it's more just we're able to see these effects that were predicted, right? So it points to, you know, general relativity and evidence for that. So support for that is where I think the excitement comes from. But does anyone have anything to add in this regard? Other than that, that's just what I think is exciting, but I don't know if there's anything more exciting.
Yeah, I think there are sort of two things that are interesting. As Shanika says, the one is just purely phenomenological. It's a prediction of general relativity, like time dilation or gravitational wave memory. But this particular kind of precession from spin-induced precession of the orbital plane is a new effect. So that's cool to see in gravitational waves, and that hasn't been, as Ilya noted, it hasn't been seen for individual binaries, but we seem to be seeing it now at a population level. But the other thing is that it is an indicator of possibly it could be telling us about formation scenarios. So because you expect things to be more nearly aligned, not perfectly aligned, but nearly aligned from field evolution, binary systems that are formed from stellar binaries, the fact that we are seeing precession is part of a growing body of evidence that at least some of our binaries that we see are formed dynamically.
Okay.
That's the thing I'm not convinced about, what you just said, that's a discerning factor, because even with, you know, primordial binaries, you'd expect misalignment.
Is it okay if I just jump in on that one, Shanika?
Yep, go for it.
So one of the more convincing things for me, Rosemary, so I agree with you that that you don't expect the spin vectors to be perfectly aligned with the orbital angular momentum from supernova kicks, but I think it's difficult to get them more than 90 degrees misaligned, which we are seeing evidence of some events with negative chi effective, which means that at least one of the spins is more than 90 degrees tilted from the orbital angular momentum. And I think that's not impossible, but that would be, and Bernard has asked a question, and he can, I saw Bernard's name. No, maybe he hasn't, but Alex or Bernard can comment on this as well.
Well,
perhaps.
you see that we do see this in massive stars and even in stars in, you know, exoplanet systems, that we see severe misalignment and even anti-alignment of the parent stars, and they're not doing any of this fancy stuff. So it's something to do with the, well, we don't know if it's intrinsic to the star, the influence of the orbiting bodies, or what it is. But
my understanding is that it's not easy in merging binaries for compact objects. Right.
Eric,
Right.
sorry, just to follow up on one thing you mentioned, you said that you do see evidence of negative chi effective, if I understood correctly, of anti-alignment. Is that a statement about, do you have any specific individual events where there's clear evidence for negative chi effective, or is that also a population level statement based on a population level model? Sorry, there's a question for Shanika, of course.
Yeah, population level. So we see this, on a population level, not for individual events.
Right, but that assumes that you believe that one of these models you have for the population distribution is the appropriate one, right? So, I mean, this is actually one of the other issues, that if I can imagine lots of distributions which have no negative chi effective, but if I make a Gaussian best fit to them, I will have some support at a negative chi effective. For example, a distribution that is predominantly has chi effective around 0, but then has a few outliers at positive chi effective, none at negative chi effective. It will have a relatively broad sigma, because if you try to fit a Gaussian into it, you'll end up with a broad sigma, and that will give you artificial support of negative chi-effective, even though not a single event has negative chi-effective.
And Ilya, as you probably would point out, there's even support for chi larger than 1 in a Gaussian tail.
Indeed.
So we have an answer to this, but Shanika, do you know it off the top of your head, or?
So I was going to say, I think there's also another plot that looks for Kaimin, but the studies that Tom has done, they looked specifically for the fraction that's positive and negative, and seeing, comparing that to the prior as well. And so I probably can't explain this as good as Eric can, so I'm going to just pass this on to Eric, but they did do this to kind of check that effect.
Is it okay if I share my screen for a second, Shanika?
Sure.
So your reaction, Ilya, was my reaction to this initially as well, that you're just detecting the width of the distribution of chi-effective. You're not actually detecting negative chi-effective when I first saw Tom's result. So we had him introduce this new parameter, chi-effective min, which truncates the distribution. And so if you only had positive chi-effective, you would expect that this would be consistent with 0. But it peaks away from 0, suggesting some preference for small negative chi-effective. I can also, this is in the paper, by the way. There are a few individual events as well that you can, if I'm remembering correctly, have like 1.5 sigma negative statistically significant chi-effective, or like 2 sigma. So there are some, there's not like a smoking gun one, but there are visibly by eye clusters of things that are kind of like anti-aligned in a suspicious way. Again, with the significance that you can kind of see from this plot. And Alex, to answer your comment, all the distributions are obviously cut off at unphysical values of chi. So we go between chi-effective of -1 and 1, and then normalize the distribution appropriately.
So do you have to use a Gaussian, or could you use a different statistical distribution that is limited between -1 and 1 instead as a basis?
Yeah, you can always do different models. So this particular analysis used this Gaussian. There was another analysis in the paper that did not work with the chi-effective and chi-p parameters. So instead it worked with the more physical degrees of freedom, the tilt of the spin angles, and the spin amplitude. These, for the non-specialists in the room, this chi-effective and chi-p are, they show up in gravitational waveform formulas. So they're kind of weird combinations of spin parameters that are, wouldn't be intuitive if you weren't working with gravitational waveforms. So we do another analysis with different parameters, and we get consistent results, but the signal is most clear in this Gaussian model. I can say maybe one other thing. I'll show you maybe one other plot. We have I don't know if it made it into the final version of the paper, maybe not. We had a version of this, a plot where we showed the chi-effective and chi-p values of the individual events plotted alongside the distribution. And by eye, it looks like the distribution is a reasonable guess for what the data are. So here's another example of a similar test where we're plotting basically showing the model and the data together to check for sanity, because one of the things that questions Ilya's kind of asking between the lines is, well, and you as well, Alex, is if you pick the wrong model, then you can draw conclusions that are true given the model, but it's just not a suitable model. And all the tests we've done suggest that the models are at least consistent with the data. So we have checked that they're not crazy. But of course, if you tried other models, it's possible you would get different results. Sorry for talking so much.
Thank you, Shanika and Eric, both for the very clear answers.
Thank you. We have another hand up from Nikhil.
Hi, Shanika and Eric. Thanks for the really great talk. I just had one question, which might show my ignorance a little bit, but how much, this comes back to what Ilya was asking at the very beginning as well. Is there any problem with robustness of this result in terms of sort of waveform systematics if you're confusing precession with eccentricity or higher order modes, because some analysis does not include those, some waveforms do not include those physics, that piece of physics.
So I think this really does link back to some studies done by some fellow Monash people. I think Isabelle did a study that on 190521, which showed that signatures of precession could be shown as eccentricity and vice versa. But in terms of a population and what we look for here, I'm not exactly sure if there's potential confusion between eccentricity and precession, given that from memory it's for really high mass, although I'm not 100% sure. Eric or Isabelle, do you have anything to add here?
I mean, just to, I'm not, so I do remember that paper, and I'm remembering that study specifically about confusing the higher, it's really in the higher mass mergers, if I'm recalling correctly. But I'm just asking more in terms of generally, not just specifically to eccentricity, because for some of these events, your preferred waveform model does not include, it's only IMR phenom PV2, which is not higher order modes, which is just precession. So do you get any, are you missing any posterior samples, as Ilya alluded to early on, just because you didn't have include all the physics?
So we definitely used higher order mode waveforms for these analyses for as the default, but beyond that, I'm not sure. Eric, do you have anything to add other than that?
Yeah, I think you're right that we don't use phenom P as a rule. We use whatever the preferred samples were, and
which were the higher order mode waveforms.
The PE folks are pretty careful about that. It's true that we did not do a systematic error analysis where we changed the waveform to the second best available approximate and then see how the results change, basically because of person power issues. I personally think they're robust because of little mini studies done here and there, which, like, for example, we would get the parameter estimation would all get redone. We'd get new samples for each event, and then we'd have to rerun everything because the preferred sample would change. The preferred samples would change, and this is something that Shanika spent a huge amount of time doing. And the plots were incredibly stable during that process. So when, like, these, you can think of these as like kind of accidental systematic error studies where you're kind of just checking if things varied a lot when you change the input. So they seem stable, at least to the approximates that we had available. The eccentricity is just, I have like no idea with that one, but I would say that if it's eccentricity causing some of these signals, that's also very interesting, because eccentricity is itself, a possible indicator of dynamical assembly. So that would be really interesting, but very hard to, adding that even though it's just one dimension, adding that is just really hard.
Awesome, thank you.
It looks like Isabelle has something as well. Chat, I just saw.
Thank you very much. So I think we've nearly used up the hour. Thanks for the really nice talk and the extensive discussion afterwards. Are there any final questions for Shanika?
I've got a very short one, hopefully.
Please go ahead.
It's more of a sort of question about the plots. There's, in the mass distribution plots, you've got a line and then you've got some shaded region. And I'm guessing the line's like the one you expect it to be, and then the shaded region is like some error interval.
Yes, I did.
But
do that.
sometimes, especially at the start, sometimes the line goes outside the shaded region.
Yes.
Why?
This is a very common question. So, and I probably should have outlined this, but so the solid line is showing the mean rather than the median. So this is the reason why it kind of veers out of what we think, what the symmetric confidence interval is. So the shaded region is the 90% credible interval symmetric around the median, and the solid line is actually the mean, and that's why there's a difference between the two. Yes, I'm pretty sure the first time around I didn't say what they were, so thanks for that. Were there any further?
Okay, yeah. Are there any other questions? If not, let's give Shanika another round of applause, or virtual round of applause.